All right. Good morning. Let's take a look at the problems that you have. The laws of logarithms are fairly basic. One of them says that the logarithm of a product, if I ever write ln, let me know if I don't catch it. There's another type of logarithm that we use in calculus, and it's abbreviated ln. But one of the one of the properties of logarithms or laws of logarithms says that the logarithm of a product is equal to the sum of the logarithms. So when you reverse engineer that, or you look at it in the opposite order, if you have the sum of logarithms, you can write it as a single logarithm of a product of the arguments. When you have a difference of logarithms, that can be rewritten as a single logarithm where you have the quotient of the two arguments. But the order in which you divide those two arguments in the single logarithm is the same as the order in which you subtract the separate logarithms. So log A minus log B is log A over B, not B over A. And then the third property, which we're going to be looking at a lot today, and I'll just pick on this piece of question 3G, says that the logarithm of a power is equal to the logarithm of the base multiplied by the exponent. And again, you'll notice there's no brackets around the 3 to the 2 in the typed version of this question. But over the years, I've kind of thought, you know what, we should have brackets around that. Those are the three laws of logarithms. Does anybody have any questions you would like me to go over? Go ahead. 10F and G. So we'll take a look at F first. Oops. What do we have? We have 2/3 log base 2 of A minus 5 log base 2 of B minus 1/5 log base 2 of C cubed. The good news is they're all base 2 logarithms. So we're going to be able to pack these together into a single base 2 logarithm. Before I do, I'm going to use the power law and write this as log base 2 of A to the 2/3. So any coefficient can be written as the exponent on the power of the logarithm, or vice versa. I'm going to write the second piece as negative log base 2 of B to the 5. And I don't have a quarrel with you. If you don't put brackets here, I think that's okay. I don't think it's really necessary. I like it though. Minus log base 2 of, it's going to get a little, well, not messy, but complicated. We need to take C cubed and raise it to the 1/5. I just want to make sure I know what it is we're doing here. It says simplify. In my mind, that means to pack it all together as a single logarithm. These are all base 2 logarithms now, so we can use the kind of shortcut rule that I told you yesterday. When you bring separate logarithms together, the new argument will be a quotient, which means a fraction, where any of the old arguments that were in positive logarithms, those arguments go on the top, and any arguments that were in negative logarithms go on the bottom. So we're going to have A to the 2/3. Then we're going to have B to the 5, and we're going to have C raised to an exponent. Now, just to talk for a second here about C cubed raised to the 5th, that's called a power of a power. And a power of a power is simplified by multiplying the two exponents together. So we'll get 3/5. And then this is our answer. Good with that one? You also said G, is that right? Okay. So G, again, just looking it over briefly here, I can see that they're all the same base logarithms. They're base A logarithms or log base A's. So we can put them together. I will rewrite this. I'm tempted to just put these all together at once, but I'll do it in a couple of steps. So I'm just rewriting the first few terms. I'm putting brackets around the entire argument because I've made a vow to myself to start doing that. I've run out of room, so I'm just going to continue this on the next line. Log base A of y to the x minus 5. And then I have minus log base A of y to the 3x plus 1 raised to the 2 because of the power law for logarithms. We can put this all together now as a single base A logarithm with a new argument that's a quotient, a fraction, where any of the old arguments that came from positive logarithms go on the top. So this is first logarithm is positive. We can write y to the 2x minus 3 multiplied by y to the 5x minus 2. And any arguments that were part of a negative logarithm go on the bottom. So we're going to have y to the x minus 5 multiplied by y to the 3x plus 1 squared means we have to multiply those exponents. This is a grade 9, grade 10 rule. It's got nothing really directly to do with logarithms. So we're going to get 6x plus 2. Now we're going to delve back into grade 10. I want to double check all those exponents to make sure, even from the beginning, that I didn't switch a sign or anything silly like that. I think it's okay. How do we simplify this? Well, when you look at the top of this argument, you have a common base of y, and you're multiplying two powers with a base of y. You have to add the exponents. That's the rule. X squared times x cubed is x to the 5 because x squared is x times x, and then x cubed is x times x times x. You've got 5 x's in a row being multiplied, so that's x to the 5. That's where that rule comes from. So we have to add these 2x minus 3 plus 5x minus 2. On the bottom, we're going to have y to the x minus 5 plus 6x plus 2. We're getting there. This is going to be log base A of, on the top we have y to the 5x minus 5. 7x minus 5. I thought I saw a 3 here. 2x plus 5x is 7x, negative 3 minus 2 is negative 5. On the bottom we have y to the 7x minus 3. Because we add x and 6x to get 7x, we add negative 5 and 2 to get negative 3. And now we're going to use the rule from grade 9-10 math that says when you divide a common base, the result is found by subtracting the exponents. And by the way, when you subtract the exponents, whatever you get is over 1. It's on the top. Which means this is going to become log base A of y raised to the 7x minus 5 minus 7x minus 3. And of course I've made a mistake here that I make a lot of the time intentionally because it's such a common error that you would hate to get questions wrong on an exam because you're screwing up with grade 7-8 math. We're subtracting 7x minus 3, so you need a set of brackets around there. Anyway, what we get is log base A of y to the, well, 7x minus 7x is 0. Negative 5 minus negative 3 is negative 2. So this is your answer. There's a lot of ways this can be written. We could write this. This is equivalent to it. I don't know what they're going to have for an answer, but on a multiple choice, I suspect that I would put that as an answer. You know what you could do as well, and I'm just going to point this out to you. If you switch the sign on a logarithm, you make a logarithm positive from negative or negative from positive, the argument will flip over. There's a reason for that, because I'll take a round trip here. This is log base a of y to the negative 1 squared, isn't it? Because negative 1 times 2 gives you negative 2. And I can move that 2 in front and put the 2 in front and have y to the negative 1, but y to the negative 1 is 1 over y. You can always flip the argument over and change it from positive to negative or negative to positive. Other questions? Go ahead, Zebby. 11G. Okay. So what I'm seeing is what I saw at the end or near the end of the last question, 10G, where we had common bases being multiplied and we would add the exponents. That means since I have root 2 raised to the m times root 2 raised to the n, I can write that as root 2 raised to the sum of those two exponents. So this new exponent on the single power will be log base 6 of 27. You'll notice the bases when things are typed are not really low down when you write them physically on paper. I tend to write them a little lower. Plus log base 6 of 16. This is over root 2 raised to the log base 6 of 12. Now when I add those two exponents, Zebby, I can use the power law, which says in reverse, the sum of logarithms is equal to the logarithm of the product. This then becomes, I don't normally like working left to right, but I'm just going to do it here. This becomes log base 6 of whatever 27 times 16 is. And on the bottom, I have root 2 to the log base 6 of 12. Now what we're dealing with is this situation. Because we have a base 2 over a base 2, we're going to subtract the exponents, which is going to give us root 2 raised to the log base 6 of what, well, I'll do this in parts. I was going to jump ahead and put it all together, but 27 times 16 minus log base 6 of 12. This whole thing, everybody, that I'm going to highlight, here is the exponent on root 2, right? It's all raised as an exponent. Now I'm subtracting logarithms so I can divide the arguments. What I end up with here is root 2 raised to the log base 6 of whatever 27 times 16 over 12 is, 4/3, 9. I believe that argument in the logarithm is 36. Am I right? So you end up with root 2 raised to the log base 6 of 36, and we should know that log base 6 of 36 is 2 because 2 is the exponent to which you raise 6 to get 36. So we end up with root 2 squared, which gives us 2. Is that okay? Any other questions? Go ahead, Ryan.
5b.
B? So we want to express this as a single logarithm. The first thing that we need to do before we combine separate logarithms into a single logarithm using the power, let me start again. I misspoke. The first thing we need to do when we combine separate logarithms into a single logarithm before we apply the product and quotient laws is apply the power law in reverse. We need to get these exponents that are currently residing in front up as part of the argument. So this will be log base a of p to the third plus log base a of q cubed minus log base a of p to the 4. Does that make sense? Okay. Now we can put them together. And again, rather than dealing with the power law and I keep saying power law. Rather than dealing with the product and quotient laws separately, we can just put them together and say, if the logarithm is positive, the argument will go in the numerator of the single logarithm's argument. So when I put these together as a single logarithm, and I can do this because it is a base a throughout every logarithm, I can put p to the third on the top. I can put q cubed on the top because these are both positive logarithms. And then on the bottom of the argument is p to the 4. And there are two p's. So there's two p's and a q. But now we can simplify p to the third over p to the 4. And normally I would say I like to cancel variables rather than taking the quotient rule for exponents, which says x to the m over x to the n equals x to the m minus n. Normally I would shy away from that rule, but since we have fractional exponents, I think it's a good idea. It's hard to visualize what cancels when you have fractions of an exponent. I think this is a good idea to just do it off on the side. You would be showing your work. This isn't scrap paper. You would be doing this right on an exam, but this is p to the third minus 4. I'm not really up for common denominators here, but you could convert them all to denominators of 3 and end up with negative 11 thirds. But I suspect that many of you would just take your calculator and figure out that it's negative 11 thirds. Am I right? Is that reasoning in my head? Correct? Okay, now remember what I said. This is nice because I just mentioned this earlier. When you use this rule, what you're getting is over 1. The result you get is in the numerator. So what we have is log base a of p to the negative 11 thirds multiplied by q to the 3. But we don't like negative exponents. So we would probably take what we learn in Math 10 and write that as over p to the 11 thirds. Is that okay? You're welcome. Okay, we are going to move on now. So we're looking, I believe, at, I don't know, I'd be guessing, so I better take a look. Page 18 of your unit handout. Tomorrow we are back to having our seminar, and we're going to have a short quiz in the seminar. I don't know, 5 or 6 multiple choice numerical response style questions dealing with laws of logarithms and what we're doing today. Okay? This is dealing with solving, this section 8.4 in your textbook is called Solving Logarithmic and Exponential Equations. I've broken it into 2 parts. Today what we're going to be doing is solving exponential equations, which we knew how to solve before if we could have a common base. These you cannot have a common base. For example, 4 to the x equals 605. Well, how do you find x when you can't write 4 and 605 as a common base? 8 multiplied by 3 to the 2x is 568. These are all exponential equations because x is part of the exponent. But you can't write 4 and 3 using the same base. So the procedure we're going to use here is one that, the procedure I'm going to teach you is one that will always work here, even though there's a different thing you could do for question A. The different thing you could do for question A won't work for other equations. Okay? And I'll show you the different thing in a second. The problem with an exponential equation, this is how I view it, is that the thing you're trying to find is in an inaccessible area. It's part of an exponent. We like variables and numbers to be on the main line. So when we write stuff, I'll give you an example here. If I were to write 2 log base 3 of x, x and 2 and log base 3 are all on the same line. I know that 3 is written lower, but the 3 is tied to the logarithm. We don't like exponents. So how do we get rid of exponents? How do we get things on the same main line? Well, let's take the base 10 logarithm of both sides. Why? Well, first of all, why can we do that? We can do that because any equation will still be in balance if you do the same operation to both sides. If you add 2 to both sides, you're still going to be in balance. If you take the square root of both sides, you're still going to be in balance. If you take the base 10 logarithm of both sides, it's still true. Now, why? Why would we do this? We would do this because now what I can do is move that x, which is really in brackets as an exponent of base 4, I can move that x in front. And what I have right now then is x log 4, which is how it's written, equals log 605. Now, I do want to just point something out to you here. Well, a couple of things. That this log 4 is just a number. This is just a number. It's a different number, so I'll just put 2 hashtags there. But it's just, those things are just numbers. Normally, when you have x multiplied by a number, it's written with the number first. Right? If you had to multiply x by 3, you would write this. You wouldn't write this, correct? So why do we put the x first? Because x log 4 makes sense. Log 4 x, I don't know what it is you mean here. Do you mean log of 4 times x? Do you mean log of 4x? What do you mean? So the x is written in front. But the bottom line is x is still being multiplied by that log 4. So to get x by itself, you take log 605 over log 4. That's the answer. Whatever that's the exact answer. Okay? Whatever this is equal to in decimal form will simply be a decimal approximation. Log 605 divided by log 4. The answer is approximately 4.62 if you wanted a decimal value. Is there a different way you could have done this question? Yes, I will show it to you, but point out to you that this won't work for the other ones. It will get more complicated for the other ones. What you could have done, going back to the top, is just rewritten that in logarithmic form. You could have said if 4 to the x equals 605, then x is the exponent, which means x is the logarithm, and it's a base 4 logarithm of 605. And then you would look at this thing, and you would say, well, how do I figure out what log base 4 of 605 is? And the answer is you would use the change of base formula. You would say that that x is the base 10 logarithm of the argument over the base 10 logarithm of 4, but that's what we got. The only problem with that, so this is where you have to go away from my advice of changing language if it doesn't make sense, is it won't work for any of the remaining questions that we're going to do today. It will work if you have a very basic exponential equation like that. Number to the x equals number. Sorry, does anybody have any questions with the work we did there in A? Okay, so we have to ask ourselves an important question here, and the answer determines the path we take. We have 8 multiplied by 3 to the 2x. That doesn't mean 8 times 3. It means 8 multiplied by 3 to the 2x. It would be nice if we could get rid of that 8 before we take the logarithm of both sides. Does 568 divide by 8? That's lucky for us, because if it doesn't, then we're going to have to deal with fractions, or we're going to have to leave that 8 out in front. Ryan, what do we get when we take, 71? We get 71. So if you divide both sides by 8, 568 over 8 is 71, and we're left with 3 to the 2x. Somebody in my Math 20 class was asking me yesterday, we've been having a lot of discussions about when you can cancel things. We can cancel the 8 because on the bottom of this, 8 is a factor, and on the top, 8 is a factor. We know 8 is a factor on the top because it's being multiplied by the rest of the top. Well, okay, now we take the log of both sides. And our whole motivation for taking the logarithm of both sides is we take a base 10 logarithm of both sides because we have access to a base 10 function on our calculator for logarithms. And the reason why we actually do this is because the next step involves moving that exponent out in front. Now, think about this for a second. If we want to get x by itself, then what we need to do is we need to get rid of this 2, which is a number, and we need to get rid of log of 3, which is a number. So we need to divide by both of those, right? Another way to look at it is if I rewrite this, and I'm not saying you would rewrite it this way, but rewrite it as x times 2 log 3 equals log 71, then that means we have to divide both sides by 2 log 3. You have to divide by the 2 and the log 3. So x is going to be equal to log of 71 over 2 log 3, or log of 71 over log 9. Because that 2 log 3, I can bring the 2 up top and have it written as log of 3 squared. And you know, some of you might appreciate this. We'll get to a decimal answer in a second, but you could have kind of done that up here. You could have said, you know what? I'm going to imagine that instead of writing 3 to the 2x, I'm going to write 3 to the 2, then raised to the x, and I'm going to move only the x down in front. And that's going to stay as 3 squared. Anyway, if we want a decimal value, it doesn't matter which one you do. I would be tempted to use the second one, because if I enter the first one, the left answer in my calculator, I do need an extra set of brackets around the 2 log 3. Or I need to go divided by 2, divided by log 3. So log 71 over log 9. So approximately 1.94. Am I right there? Did anybody else get approximately 1.94? Okay, just checking. So now all of a sudden things are going to get more complicated. This is pretty complicated. I have to take the logarithm of both sides, so I'm going to have log of 4 raised to the 2x minus 1. These are base 10 logarithms, equals log of 3 raised to the x plus 2. Now, the power rule for logarithms says that if I take the exponent on the argument and multiply it by the logarithm of the base, that's the same thing. But the exponent of the argument is a binomial. If I just write that, I'll even make it more obvious as to the mistake. If I write that, it looks like I'm saying 2x minus log 4. And that's not what I want. What I need to be saying is 2x minus 1 multiplied by log 4. And this will be equal to x plus 2 multiplied by log 3. So now, how do you get x by itself? There's something we have to do here that's very specific to this type of equation. You're only going to encounter it in one other area in high school math. If you take calculus, when we find what's called an implicit derivative, you end up having to do this same procedure. You have to first of all multiply this whole thing out. So we have to take that 2x minus 1 and multiply by log 4. We're going to get 2x log 4 minus 1 log 4. The 1 is obviously not necessary. Equals, and we're going to do the same thing on the other side, x log 3 plus 2 log 3. Which, by the way, you could write 2 log 3 as log of 9 if you wanted to, but I'm not going to do that just yet. Then the next step is you have to say to yourself, forget about logarithms. Just look up here for a second. Log 4 is just a number. Log 3 is just a number. This equation that you're looking at, even though it has logarithms in it, is a linear equation. It's got terms that have x and it's got terms that don't have x. There's no x squared, it's not quadratic, it's just linear. You have to move all of the terms that contain the variable to one side and all of the terms that contain no variables to the other side. Does it really matter which side? I usually move things to the side where fewer negatives result. Okay. So if I were to move my x terms to the right side, please don't write this down. If I were to move the x terms to the right side, I would get x log 3 minus 2x log 4 equals negative log 4 minus 2 log 3. Look at the whole slew of negative numbers I've introduced. Now, sometimes what's going to happen is if you move it to one side or the other, you get the same number of negatives. And we'll deal with that when the time comes. So this is kind of it doesn't really please me. What I would rather do is move the x's to the left side where I collectively get more positive terms. I'm going to have 2x log 4 minus the x term from the other side, x log 3, equals, I have the 2 log 3 here, and if I add the log 4, this is mathematically more pleasing to me. It wouldn't be wrong if you did what I wrote in green. Let's just double check to make sure I've transposed everything correctly. I think it looks okay. We in agreement? Okay. So, again, from this line at the top of the screen, you have to do two very specific things so far. You need to expand it out, then you need to collect all of your x's on one side and your numbers on the other, and then there's a third thing. But this is a little bit more involved, because even though log 4 and 2 are just numbers and log 3 are just numbers, you're not used to seeing numbers that way. If I had this, if I had that, if I had 18 as the number times x minus 3 times the number times x, it's pretty clear it's 15x, right? I hope. But it's not clear what this is. So instead, you factor x out. By factoring x out, you get x almost by itself. You no longer have two x's. If I factor x out, I get out of the first term 2 log 4 minus log 3. And let's face it, if 2 was just a number, log 4 was just a number, log 3 is just a number, then 2 log 4 minus log 3 is just a number. That's all it is. It has a value that's probably important in this question, but it is merely a number. So if you had, x times 12 equals 70, you would divide both sides by 12 to get x. So what we have to do here is write that x is equal to 2 log 3 plus log 4 divided by 2 log 4 minus log 3. So any questions with the steps there in getting that? Let's talk about an exam. Math 30 exams can be really dirty, like challenging. You might be given this as a numerical response and told that x is equal to a log b plus log c over a log c minus log b. What are the values of a, b, and c? You have to be able to cope with that. By the way, could I write this answer as log 9 plus log 4 over log 16 minus log 3? Sure, I could bring each of these coefficients of 2 on the logarithm on the top and the logarithm on the bottom. I can move them up as exponents and take 3 squared and 4 squared. Could I write this as... And by the way, this has nothing to do with my numerical response illustration. I think it would be difficult to pack this into a numerical response because of the fact that it's 16. It's not a single digit. But could I write this? Well, sure, because I hope you see log 4 plus log 9 is log 4 times 9, which is 36. Why would I not pack these two logarithms together as a single logarithm on the bottom, though? I could. Anybody have an idea of why I wouldn't want to do that?
You don't want another denominator?
Yeah, 16 doesn't divide nicely by 3. It doesn't divide without remainder by 3. So you would have a complex fraction of sorts. If you want to calculate that, you can use your calculator. Let's look at the final example. Now, this is very similar to B. B, remember, we had that 568, and then on the other side we had 8 times something, and we could divide both sides by 8. You can't divide both sides by 24 here. Well, you can. It just doesn't get you anywhere. You just move the 24 to a different side of the equation. So we have to take the logarithm of both sides as it appears right now. Now, can I move this x plus 3 out in front and multiply that by the base 10 logarithm of 2? Definitely. Can I move the exponent on the left, that x plus 2, out in front? The answer is no. This rule, which I'm going to write down that we've been using, says log base whatever of m to the n is equal to n times log base whatever of m. You can only move that exponent in front if the logarithm is of an argument that's only that power, m to the n. This 24 is mixing things up for us. We can't move that exponent out in front, but what we can do is say that this is log of 24 plus log of 6 to the x plus 2. So I'm using the product law to separate out those two logarithms, and now that second logarithm in the line that we're at does qualify. This logarithm here does qualify for using the power rule. So I can write this now as log of 24 plus x plus 2 log 6 equals x plus 3 log 2. So where are we at? What we've done is we've finally got the exponents down on the main working line mathematically. How do we get the x by itself? We have to expand it, move all the x terms to one side, non-x terms to the other, then factor x out of all those x terms and divide by whatever we have left. Maybe I'll take a break here. I'll tell you right now that typically speaking, and it's been a couple years since I've had a chance to see a diploma exam, this is almost always, this type of question of taking logs of both sides and solving for x, is almost always in the written portion of the diploma exam. And it's always in the written portion of my exam. It's important. Okay. So let's expand this out. Important meaning we feel it's an important enough skill that we're going to make sure we test you on it. So x times log 6 is x log 6. 2 times log 6 is 2 log 6. I hope that many of you are just seeing 2 log 6 as log 36. Like you just see it and you go, oh, well, that's log of 36. And then equals x log 2 plus 3 log 2. 3 log 2, by the way, is log 8. Because if you move that exponent up in front, that's in front currently, and put it up top on the base of 2, you'll have 2 to the 3. 2 to the 3 is 8. So what are our x terms? Our x terms are x log 6 and x log 2. And everything's positive here. I hope it's obvious that when we move stuff to the left, you won't have as many negatives as if you move stuff to the right. Let me repeat that, because that was very ambiguous. I hope it's obvious that when you move all of the non-x terms to the left, you have fewer negatives. Because you already have 2 of the 3 numerical terms on the left, and they're already positive. So let's leave them on the left. Log of 24 plus, I really want to write log of 36, but let's see how this breaks down. Then, so it's 2 log 6 or log of 36. I have to subtract 3 log 2. This will be equal to x log 2 minus x log 6. Double check every single term. I think it's okay. Again, remember what I've told you as the algebra gets more difficult in high school math. Every step is 2 steps. Every step you do and you double check. Or you do a few steps and then you double check your work. I can factor the x out of the right-hand side and have log 2 minus log 6. This is equal to log 24 plus, I'm going to put these up top now. I'm going to write 2 log 6 as log of 36. And 3 log 2 is log of 2 to the 3, which is log of 8. I don't know if many of you are appreciating what I'm about to say. But when you stop for a second and look up here, I think this is going to be a good idea because 24 divides by 8. If we were to pack all this stuff together as a single logarithm, we'd have 24 times 36 over 8. 24 over 8 is 3, so it would be log of a single number. It would be a nice thing to see. The other side is a little more complicated. So x is going to be equal to log 24 plus log 36 minus log 8 divided by log 2 minus log 6. This is our answer. If you want to evaluate it, then you're going to have to do some practice here later today where you will make sure you know how to use your calculator to get the right answer. I'm not going to spend time doing this. Could we write this in other ways? Well, yeah, we could write this as log of 24 times 36 over 8 over, I'm going to leave the bottom alone right now. How many of you suspect there's something you can do with the bottom? Maybe. We'll get to that in a second. 24 times 36 over 8, I believe, is 108. So this becomes x is equal to log 108. Let's pause there. Do you have to do this? Well, it depends. The masks need to be traded for other masks sometimes on an exam to find the appearance of your answer that matches the question. Now, I think this is acceptable, but the bottom of this expression is log of 2 over 6, right? Which is 1/3. Do you agree it's kind of a shame that it's not the other way around? If it were log 6 minus log 2, that would be good. Because log 6 minus log 2 is log of 6 over 2, which is log of 3. Well, we can make it the other way around. By factoring a negative 1 out, the log 6 becomes negative, the log 6 becomes positive, the log 2 becomes negative. Log 6 minus log 2 is log 3. It's log 6 over 2. Which means we could have, if you really wanted to be economical in what you write, the following. Negative log 108 over log 3. Oh, hey. So are we good to there? Does 108 divide by 3? 36, right? So is everybody okay with me writing negative log of 36? I sure hope not. Because there's no rule that says when you divide logarithms, something happens. There's a rule for adding logarithms. There's a rule for subtracting logarithms. There's not a rule for dividing logarithms. There's a rule for dividing arguments in a single logarithm. So don't get carried away. Practice problems. There's 2 problem sets in the handout on page 34. There's 2 problem sets suggested in the textbook on page 412. I'm going to hand out your next assignment, which deals with population growth and decline. But when we first did population growth and decline, you remember we had to solve the equations that we developed graphically? That's because the exponents were inaccessible to us. Now they are accessible. So when you get this assignment, which is due, I think it says Thursday. I'll take it Friday, though. When you solve the equations in this assignment, you need to do it algebraically, which means doing this. By the way, we will finish the unit tomorrow, which is Wednesday. We're going to review 3 days in this unit. We have time, okay, and we're getting very close to the end of the course, and I really want you to do well here. I don't want to have people be discouraged because you don't do well on this exam. That means that our exam will be Tuesday, and if my calculations are correct, Tuesday is a seminar day, which would mean our exam is written from the seminar into period 2. Wednesday is our seminar, Thursday, Friday, Monday, that's correct. So get to work on these problems. I will hand out your next assignment, which is going to be due Friday, and our exam is next Tuesday.